understand anything, but thank you anyway. As my talk is going to be a little bit long, I prefer to start with the end, with what I had planned to show you at the end, in case I don't have time after. So let's start with something else, because as Anna said, I guess, I'm also vice chair of a big European network involving 28 countries at the moment, and you are part of this as well. So this is the COST network. So here are the countries represented in this network. What I want to draw your attention is that Hubert Hebert in Munich and myself in Rennes are chairing this network. So the South Federal University is part of this network. That means that you can benefit from a certain number of possibilities that we offer, and well, just for the researchers and for the PhD students. So I would advise you to try to get missions or to attend to schools if you are interested. No, it is this one. Okay, I don't know if you see very well, but one of the things you can apply for is short-term scientific missions. So here you see Russia is considered as a near neighbor country. So you are allowed to host missions, and you are allowed to go to apply for a funding for a mission to go to any of the COST countries which are within this network. I mentioned as well that we organize 4-day training schools to practice the use of computer codes related to spectroscopies. So the first 2 training schools have been held in the Czech Republic with the codes Abinit, SPR, KKR, and a quantum chemistry code which is Quanti. The second one was held a month ago in Slovenia, and it was Vin2K, Quantum Espresso, and Orca. And myself, I will organize the next training school in Rennes, in France, on multiple scattering codes. So I'm not sure you can read everything here, but you are entitled both to give lectures of these talks and to attend the talks as trainee. So this is just what I wanted to say, and this can apply to researchers and PhD students, but not to master and undergraduate students. Just briefly, the training school on multiple scattering codes will be held the last week of June, and it will feature 5 codes, MXAN and GNXAS, which allow to model X-ray absorption. My own code, which I will discuss in a minute, MSspec, which can deal with X-ray absorption as well, but photoelectron diffraction and Auger electron diffraction and other spectroscopies. And FPMS, which is a full potential multiple scattering code, and MCMS, which is multi-channel multiple scattering codes. So here briefly, I will leave you there, so I don't go through the details, but here is what we will do during this talk, and then during these 4 weeks, and then we will have an MSNano conference. So Anna mentioned, I guess, that yes?
Excuse me, who and how can participate in this group?
Anybody starting from PhD up. So if you're a PhD student or a researcher, you can participate. Anybody can participate, but you can get funding to participate.
Thanks.
Okay? Then there will be the MSNano conference, where myself and Anna Taranukina will give talks, and we will finish on the Saturday by a conference to honor Rino Natoli at the occasion of his 75th birthday. Rino Natoli was one of the pioneers of multiple scattering in Europe, and many people such as Chuck Fadley or Michel Van Hove or John Rea will come to attend this tribute conference. So now I go to the point of my talk. Sorry. Okay, so this talk will be. Is it okay when I'm far away from the microphone, or you prefer me to be in front of the microphone?
Okay,
that's okay. Okay. Just one thing: you can interrupt me anytime. Okay. Just don't wait for the end and lose track of what I'm saying. It's better to ask your question.
You can't use microphone because this loud.
Okay. So, so my talk will be about the multiple scattering approach to the modeling of Plasmon loss processes in photoemission. So briefly, after an introduction on this type of spectroscopy, I will present the computer package that I've written with other colleagues, and in which this spectroscopy will be implemented. I will, for those of you who are not, who do not know, are not used to multiple scattering theory, I will give you just first general ideas and then the basic knowledge on multiple scattering theory. Then I will, the big part of the talk will be the multiple scattering description of this Plasmon loss photoemission, and then a short conclusion. So, as you all know, a standard experiment in physics is just to shine a particle onto a sample on which you want to get information, and to collect an outgoing particle which is not necessarily the same. And you expect to get information from the collection, from the analysis of this particle that you collect. You want to get information about the sample. So the incoming particle is not necessarily the same as the outgoing particle, and it can be any type of particle. And so from this, you want information on the sample, or in our case, I come from a surface and interface physics group, on the surface or the interface between two samples. So to give you an example of the many types of spectroscopies that we can have, if we take an incoming photon here on our sample, so many effects can arise into the sample. You can just do a scattering, elastic or inelastic scattering. You can do X-ray absorption through, for instance, through transmission. You can excite electrons, and this is what I will focus on, and collect the photoelectrons. But of course, these photoelectrons that you eject from the atom, they will leave behind them a hole, because not necessarily a core, but I will discuss essentially core spectroscopies after. They can leave a hole, and the system will not like very much to have a hole, so you will have decay channels, so you can have emission after of Auger electrons or of fluorescent photons. So the spectroscopies with an outgoing electron are essentially a photoemission, angular result photoemission, or Auger electron spectroscopy. And then if you measure photons outside, you can have X-ray absorption, X-ray diffraction, or resonant X-ray scattering. So I will discuss now only photoemission. So for those of you who don't know much about photoemission, just a few sketches to remember what it is. So you shine some photons onto a sample. As I said before, these photons can excite electrons, and you measure, using an energy analyzer, you measure these electrons. Most of the time, especially when you are interested in surfaces, you need to have a clean surface. That means that you need to use ultra-high vacuum. Well, here it's written 10 to the minus 7 millibar, but in general it's more in the 10 to the minus 10 if really you are interested in the surface. When you do this, you can have, if you vary the energy of the electron that you collect, then you can see appearing some peaks which correspond to the excitation of core level. So in this case here you've got a gallium 2p peak, here you've got silicon peaks. You can have secondary electrons, which are electrons which have suffered some losses. And you can have Auger electrons that appear as well, and at the end you will get a signal coming from electrons excited from the valence band. An important point in this type of spectroscopy is the inelastic mean free path, which is basically the average distance an electron can travel without suffering a loss. And if you look at the shape of this mean free path as a function of the photoelectron kinetic energy, you see that it has a minimum around 50 eV, where its value is around 4 to 5 angstrom. So this means that if you have electrons, if you collect electrons of about 50 eV, these electrons will essentially come from the first layers, from the surface and the first layers of your sample. So this will be the favorite energy range in order to study surfaces. If you go to higher energy, let's say 1000 electron volt, 1 kilo electron volt, then you can have a mean-free path of about 20 angstrom. So in that case, you will be much more sensitive to bulk properties. So in the end, what we will do is monitor one of these structures as a function of the angle or the energy in order to obtain crystallographic, but you can also obtain electronic structure information on surfaces, interfaces, adsorbates, and so on. So if you look more closely at core level peak, you can see some other structures that appear here in the case of silicon or in the case of aluminium, and these structures here correspond to electrons that have suffered a loss, so that have been excited on a given core level. So here, for instance, the silicon 2p, but they have suffered a loss through the excitation of plasmons, which are collective excitations. So here you see these electrons have excited one plasmon, these electrons have excited two plasmons. Likewise for the aluminium, but I showed aluminium as well because you can make the difference between bulk plasmon and surface plasmon. So this can be interesting in order to study the plasmons. So what are you have basically two types of plasmons. You've got intrinsic ones, which are created by the sudden appearance of the core hole. When you eject the electron, you leave a core hole, and so you'll have a charge that will appear, and the delocalized electrons, the valence electrons, for instance, will react and try to screen this charge. So this will excite intrinsic plasmons. And likewise, your photoelectron, when it escapes, it's a charge that is moving within a media composed of delocalized electrons. So again, these delocalized electrons will react, and the photoelectron, the escaping photoelectron, can lose energy by exciting plasmons, so collective excitations of these electrons. So plasmons are boson-like collective excitation. They are the response of the system to the sudden appearance of a charge. So here, two types of charge, a core hole charge and a traveling photoelectron. Therefore, they are related to the dielectric function of the system. So the idea of this spectroscopy, which we will call photoelectron energy loss spectroscopy, is to monitor one of the plasmon peaks as a function of the energy or the escape angle, exactly as we do for the core peaks, but in order to gain this time information on the dielectric function. So this is what we are trying to model, what I want to show you, how we come, how we solve the problems in order to model this spectroscopy. So now I move to the package which I have written, the MSpec package. MSpec is for multiple scattering and spectroscopies. So the characteristic of this package is that it describes spectroscopies in which it is the electrons that is the probe of the sample. So it can be a real electron like photoemission, photoelectron diffraction, OG, low energy electron diffraction or electron energy loss spectroscopy, or more fancy spectroscopies. It can be also a virtual electron like in X-ray absorption or resonant X-ray scattering. But in all cases, as I've said, there is a common feature, is that it is the electron that probes the sample. That means that you can describe these spectroscopies using a common description, which is the multiple scattering of the probe electrons, of the probe electron or electrons, by the atoms of the sample. Probe electrons, like it can be, for instance, in photoelectron diffraction or lead, there is only one electron involved. In electron energy loss spectroscopies, there are 3 electrons involved in the physical process. So this is what we are going to do in the case of photoemission energy loss spectroscopy, because here again it is an electron that will sample probe the sample. So in the package, at the moment there are 5 spectroscopies available: photoelectron diffraction, so basically it's photoemission. OG electron diffraction, X-ray absorption, lead low energy electron diffraction, and a more fancy spectroscopy, which is OG photoelectron coincidence spectroscopy. So it is a spectroscopy where you measure in coincidence the photoelectron and the OG electron that come from the same ionization process. So in coincidence, that means within basically 10 to 20 nanoseconds. If you measure in two different detectors these two electrons within 20 nanoseconds, you can be pretty sure that they come from the same ionization process. There is another tool, but I won't discuss it, to check the convergence of one of the algorithms. So there are three algorithms to compute one of the key quantities in multiple scattering, but I will come later to the definition of this quantity, which is called the scattering path operator. So there are three ways to compute it, but they don't, they overlap slightly. I mean, they are energy dependent. Depending on your energy range, you will favor one or the other of these algorithms. There is a spin version, there is well, this I don't mention, and there is a well-documented user's guide, which is over now, at the moment it's over 250 pages. Different types of scans, so you can azimuthal, polar, full angle, or energy scans. There is an old parallel version, and you can import some external potential, but this is still under development. I will mention it later. Soon we will be able to import potential from the VASP code or from the Gaussian code for molecules. So there is a very basic graphical interface, which is represented here. So you launch it by double-clicking on the icon, I don't know. There is, so here is another view of the different windows of the graphical interface, but actually there is a new one based on Python, which is under development. Actually, I've got two colleagues, two computer engineers in Rennes who are working on this code in order to provide it with a beautiful and very convenient graphical interface. So soon it should be ready. I think for the summer it should be ready, this new graphical interface. So this is sort of a summary of the actual version. So I mentioned the 5 spectroscopies, the 3 algorithms. You can generate as well molecular crystals, nanotubes, fullerenes, and so on. There is an R-factor analysis to compare your calculations to experiments. It goes even well beyond R-factors as well, actually. And we are developing at the moment new spectroscopies that should be implemented into the version, I think, before the summer as well. So a resonant elastic X-ray scattering, I'm doing this with my former PhD student who is now working in Beijing in China. With another Chinese student we are developing electron energy loss spectroscopy. With a colleague in India we are developing E2E, the modeling of E2E within multiple scattering, and I have a postdoc who is working on STM and beam within this same framework. Okay, there is a new algorithm in view, and what I mentioned, an interface with the VASP code and Gaussian code in order to import their potentials. Because of course you need a potential to describe, to do multiple scattering. Okay, we do it, I will show it in a very basic way. So it is sufficient for most applications, but for some of them you need a very fine detailed potential, and in that case it's better to use an ab initio code, because okay, this is their job, this is not our job, so we won't reinvent the wheel and do worse than they did into our code. So it's useless, so it's better to get from them what we need. A few examples. For instance, this is photoelectron diffraction. So photoelectron diffraction, again, is just photoemission, and you monitor a core level peak in that case as a function of the escape angle of the electron. So in that case, it's the polar angle. This is just a comparison between different algorithms. So you've got matrix inversion and series expansion. I won't go much into detail into this because it's not very important. So this is just different. I want to spend a little bit more time on a practical example. So this was done during the PhD thesis of Thomas Jaouen, who finished his PhD in 2012. So the idea was to write photoelectron diffraction, actually in that case it's Auger electron diffraction, to use it, to check first if we could use it as a tool to study the interface between two systems. So in that case, that was the interface between magnesium oxide, 3 monolayers of magnesium oxide, and silver 001 surface. So this is a sketch of the system. So what my colleagues in the experimental group did is just to monitor the core levels coming from magnesium KL23, L23 peaks, and monitors them as a function of the escape angle. So here you've got this magnesium peak, so as a function of energy, for an escape angle of 45 degrees, or here I don't read, 20 degrees and 0 degrees, so along the normal. And actually what they could do is show that they could separate this contribution into 3 different peaks, which they associated to the position of the magnesium atom from which the electron comes. So C1 corresponds to electrons coming from the first layer here, above the interface, C2 coming from the second layer, and C3 from the third layer. So the idea was to get a probe that could resolve layer by layer your structure. So when they decomposed these different peaks into 3 peaks, and then they monitor the theta variation, the escape angle of each of the 3 peaks. And here are the results, the experimental results on the top plot here. You see that the variations of the C1, so electrons coming from the first layer or coming from the second or the third layer, are completely different. Okay, and they did actually, it's Thomas Jaouen who did some calculation with my code, and actually you see the comparison between the experimental results and the multiple scattering calculation. It's pretty much the same. So this was important because, of course, the tricky key point is to decompose this peak into 3 components. One first layer, second layer, 3 layer. So this validates the experimental decomposition. So this was the first step. First, to validate the technique, to say, okay, with this technique we are able to resolve layer by layer. Then we can go to do real work. Real work that was studying the incorporation of magnesium at the interface. So they did the experiment to send a beam of magnesium atom onto the system. They made the assumption that the magnesium atom will be preferably absorbed at the interface, and they wanted to know where exactly at the interface this magnesium atom will be absorbed. So they did exactly the same type of experiment. So they had here their magnesium KL23, L23 peak, and they decomposed. In that case, they were not able to decompose it into 3 peaks. They needed a 4th peak, which they called C0, and which they identified to the magnesium atoms that had been incorporated. So coming from the outside beam that had been incorporated at the interface, okay? And of course, as they wanted to know the position of these magnesium atoms, they studied the angular variations of this C0 peak as a function of the escape angle. So it is here, okay? This is the experiment. And then they used again the code to the multiple scattering code in order to model different type of structures and see if they could fit this experimental curve with a calculation. And you see here, this calculation is almost exactly the same. And so we were able to deduce that actually the magnesium atom that were incorporated at the interface were incorporated 2.10 angstroms below the last, the C1, the last magnesium oxide layer. Okay, so this was published in Physical Review Letters less than 2 years ago. So just to show you an example of how we can use this type of calculations in order to gain information on practical problems.
Sorry, may I ask some
Yeah.
practical question? For instance, if you have not 3 monolayers but 10.
10, it will be more difficult, but they managed to do it with 4.
Yeah, but I mean, in this case, I assume that you will have broad shape, and it will be just.
I'm not sure you'll be able to resolve the 10,
because
the 10 components. No, it would be very difficult. But they managed to do it with 4. I don't think they went further than 4. But of course, the more layers you have, and the more complicated it is.
devices, mistake of one point.
Yeah.
My question is, if you have, for instance, the technique to calculate, so you can't resolve your peaks, but how do you have some ideas how you can solve this problem only from calculations, not from measurement, but probably
Yes, actually, yes, it is done very often for core level peaks. Usually for core level peaks, what we do is separate the bulk and the surface components. And sometimes we've got subsurface components as well. But when you look at the peak, most of the time you don't see. You just see one single peak. But of course there have been people who have, theoreticians who have done calculations to measure the core level shift, because there is a shift, you see, between these different components. Because they don't have, the atoms don't have the same environment, the kinetic energy of the escaping electron is slightly different. Okay? So when you know, and it has been calculated for a lot of different compounds, when you know the core level shift, then you know where to position your peaks. And the shape of the peak is pretty well known as well. As far as I remember, the maximum I've seen in the literature was a decomposition of a peak into 7 components. Okay, you can, just an example, you can as well with the code image lead. So this is a comparison between, well, slight difference in energy, but it doesn't change much at this energy. Now, I come to one of the two big parts about multiple scattering theory. So, I assume that not all of you know a lot about multiple scattering, so I will first go slowly about multiple scattering, just give you a flavor of what it is, and then we will go a little bit into the more details into the mathematics. So we could define a multiple scattering theory as a reformulation of a wave equation in the presence of obstacles in terms of green functions. So I've used the word obstacles and not atoms because multiple scattering theory, as I will show it in the next slide, is used in many different areas of physics, not only for people studying atoms and clusters and materials, okay? So you've got a wave function or any type of function, differential equation like this, where L is your differential operator, and this is the eigenvalue and this is the eigenvector. In that case, you can recast your equation in terms of the green function, which is defined by z minus L to the minus 1. So with this, you can define two ingredients, and with these two ingredients, you can develop your multiple scattering theory. These ingredients are the propagator of the wave, in the absence of the obstacle, so we call it free propagation. In mathematics, in mathematical physics, it's called resultant, and it's purely a characteristic of the wave equation. And then you've got the transition operator T, which describes the effect of the obstacle on the incident wave, on the incident free wave, okay? And these operators, of course, are characteristics of the obstacle. So multiple scattering is basically the combination of these two in order to describe a physical process. What kind of physical process? Well, many of them. So, for instance, if you take the Helmholtz steady-state wave equation, so with the nabla square, phi plus k square, phi equal something which depends on phi. Okay, this will apply to the Schrödinger equation, to the time-independent Schrödinger equation. This will apply as well to the acoustic wave equation. So if you look in the literature, people working in acoustics, they use a lot of multiple scattering as well. And it's exactly the same equations as those that we are using. The heat equation as well. If some of you, I don't know if some of you, especially the young ones, are interested in surf, are going to the beach, to the sea to do surf. Surfers are interested in the long waves in the sea to practice their sport. The long wave equation in water is related as well to this. The Maxwell equation, the vector potential and the scalar potential satisfy as well this type of equation. And under certain assumption, for earthquakes as well, for seismic waves, you can end up as well with this sort of description. So just to show you that from now on I will talk about atoms, but you can use the same description for many other physical processes.
But heat equations, why you pure wave? Where are your losses? Where are your losses for temperature? Yes.
Yeah, well, in case you have, I don't know, but
I never have listened that
uh,
it's possible. It's possible.
yes,
The equation is a wave.
yeah, you are right. But here, for instance, for sonar or things like this, you can treat it as with
Very
multiple
strong
sketching.
approximation.
Здесь нет аппроксимации никакой. Простите, это азы теории растений дают. Пока
Да,
свободная
азы
функция
теории
гена.
растения не бывают азами, если ты используешь уравнение для температуры. Для температуры волнового уравнения в таком виде нет. Там есть все-таки диффузия, там есть какие-то, ну, не вторая производная, не градиент. Не стоит квадрат второй производной.
Okay, I'm not expert at all on it, so you must be right. So, just to give you a simplified idea about multiple scattering. So you take a pinball, okay. So now you've got your incoming electron. You've got here your electron detector, okay. Then what else do you need? Well, here is your electron. If you measure the electron, so the electron must escape, so you've got a surface barrier to take into account. Here you've got your atoms. You can have, and this is what we will see in the rest of my talk, you can have inelastic losses, like emission of a photon, in our case it would be Plasmon. And at the end you put all this in the computer, and here you've got the cross-section. So basically this is what multiple scattering is about. So let's go in more details now into the mathematics and the physics of multiple scattering. So we start from the Schrödinger equation. So we suppose that we know H0. I will make a few assumptions on the potential. I will suppose that is centered at the origin, so that it's always possible to do it. But I will suppose it's short-ranged and real for simplicity. Actually, you can develop a multiple scattering theory for long-range potential, like Coulomb potential, but it's more complicated. And anyway, in atoms, short-range potentials are very good. In atoms, sorry. In solids, short-range potentials are a very good description of because you've got a lot of screen. I will define phi as the eigensolution of my H0 Hamiltonian, and psi the eigensolution of H with the same eigenvalue, because I will consider only elastic scattering. So, as I introduced a little bit before, the green or the resolvent or propagator. So I define it g of z as z to the minus h to the minus 1. So you see easily from this definition that the eigenstates of the Hamiltonian are also eigenstates of g, and that the eigenvalues of h are poles of g, which means that g contains exactly the same information as h. So you can exactly extract the same information. So scattering theory usually calculates g, while usually people, for instance, people who do electronic structure calculations, usually they solve the Hamiltonian, but you can do it as well. And this is typically what KKR does. You can do it by solving the propagator g. Now, of course, you see from this definition that if z is an eigenvalue of h, you've got a problem in your definition. So when this is an eigenvalue, you have to use a slightly different definition. You have to approach it either from above, plus, or from below. Okay, and then go to the limit. I won't demonstrate it, but G plus, so the solution with plus, describes the propagation of an electron in the usual sense, with the normal direction of time, while G minus corresponds to a time reversed process. There are two fundamental equations in scattering theory, which are Dyson equation, which relates the propagator in the presence of a potential in terms of the propagator without the potential, and the Lippmann-Schwinger equation, which does the same for the eigenstates. Okay, this formulation has an inconvenient. It's not very convenient, this formulation, because you've got the unknown on both sides here. So what we can do is, yeah, sorry, I forgot to say. So this is the scattering state. This is the incoming state and the scattered state. So the physical interpretation is very simple. So propagation in the presence of the potential V, you can decompose it into free propagation or free propagation until you find the potential T, then you are scattered by the potential T, and then you can, your electron, because now I will only deal with electrons, can travel again. So one of the possibilities, because you've got, because you've got the unknown on both sides, is to iterate. So you can replace G by the same formula. So if you do this, you will get sort of a Born expansion. You can factorize, in which case you'll got an inverse to calculate. But usually we introduce a new tool, which I mentioned before, which is the transition operator, which we just defined by this. And this gives you the relation between this transition operator and the potential. So when you use this transition operator, you can recast your Dyson equation simply like this. And the Lippmann equation, you can write it as a sum of this incoming state and the scattered state. So it has, as I've just said, it has a very simple interpretation. And now you've got the unknown, which is T. Because once you know T, now you know G. Later, when I will discuss the Plasmon, I will also use another operator, which is the molar wave operator, which is an operator that maps the unperturbed states onto the scattering states, or the free electron propagator onto the full propagator. This is just, in order to get it here, for instance, you just factorize I plus G0T, which is the value of this molar wave operator. Of course, this so far I've just introduced the scattering, this transition operator as a convenience, but it is related to things that you know well from quantum mechanics. So if you take the matrix element of this operator into spherical waves, then you get something which is related to the phase shifts of the potential of the L wave. On the potential V. If you take the matrix elements of this transition operator between plane waves, then you get something which is proportional to the scattering amplitude or scattering factor. So you see that T is really describes the scattering of the electron by a potential. And there are easy ways to calculate, because calculating the phase shifts or calculating the scattering amplitude is something that is well known for a given atom. So far I had only one potential. So multiple scattering, as the name indicates, deals with multiple atoms. So now I will consider that V is a collection, describes a collection of potential distributed all over the space. So, as I mentioned before, I made the assumption that V is at the origin of space in the previous description. So what happens now when the different V's are located at different positions of space? Well, one easy way to take this into account is to use translation operators. Okay, so we will write V as a superposition of these potential translated potential operators. So this is the origin-centered potential, and the interpretation of this is very simple, because we've seen in the previous slides how to solve scattering theory when we've got the potential at the center of space. Okay, so we have the potential located at a given position, so we translate the location to the origin of space. Once we have on the origin of space, we know how to do it, and then we put it back to its actual position. Actually, for those of you who are familiar with the addition theorem for wave functions, this is exactly the equivalent for operators. We've written V as a superposition of atomic potentials. Now, unfortunately, T is not a superposition of atomic transition operators, the T of the total system. Actually, it is a superposition of distorted transition operators, because on each atom you will feel, you will be influenced by the surrounding atoms. So there is sort of a distortion. So you have to write the transition operator in this sum as the atomic operator times a distortion due to the surrounding atoms. If there is this distortion due to the surrounding atoms, that means that this Wi can be written as a sum over J, over all the atoms of something. So this allows us to actually introduce this new quantity, which is called the scattering path operator. And that means that we write T as the double sum over I and J of the scattering path operator. So I will come in a moment why it is called scattering path operator. But I just want to say now that this will be our key quantity, and this is the key quantity that is computed into the code. Because once you know this quantity, once you've got ways, you've developed algorithms to compute this quantity, by double summing you get your transition operator. Through the Dyson equation, you get your green function, and through the definition of the green function, you can go to the Hamiltonian. So that means that once you know this, you've solved your problem. So what we will do is just to recast all what we are interested in, the cross-section of spectroscopies, in terms of this particular operator. So why is it called scattering path operator? So I remind you that T was expressed as V plus VGV. So it's easy to check that tau Ji can be written like this. If you double sum over Gi, here you will get V, here you will get V, VGV, okay? So now that you've got this expression, you can see directly a simple interpretation, because here you start from atom I. I've got my electron on atom I. G is the propagator of the full system. So that means that this operator describes the propagation of one electron starting from atom I and to atom J, and in the meantime it will be scattered by all the atoms, okay? Because G contains all the influence of all the atoms. That means that this scattering path operator describes all the possible ways the electron can travel to go from atom I to atom J. So here again we've got a very simple interpretation. Simple interpretation, but it's not very convenient for practical calculations. As I said before, we prefer to work with transition operators. So we can recast this expression. It's not easy, so I don't show you how to do it, but we can recast it into equations in terms of the atomic transition operators. So this is what we call equation of motion, because we propagate this tau here. And this equation of motion is very important, because just by looking at it, you've already got two ways to solve your problem, two ways to compute the scattering path operator. Of course, you can iterate, okay? You can replace tau ki by this formula. If you do this, you get what we call the multiple scattering series expansion, okay? So you see that to go from atom I to atom J, you can just go directly. G0 is the free electron propagator. Or you can go by, the electron can be scattered by one intermediate atoms. This, we will call it single scattering, etc., etc. It can be scattered by two atoms, and so on and so forth. And of course, it goes up to infinity. Now, this is a perturbative expansion, so you have to be careful, and it doesn't converge all the time. So you can have divergences generally below 50 electron volts, but even for higher energy you can have divergences. So this is an algorithm that is suited to higher energies. The other way you can consider this equation is to say, okay, this is a matrix equation. If I define the matrix of tau, the matrix of T, and the matrix of G0, I can recast my expression like this. tau equal t minus 1 minus g0 to the minus 1. Okay? So I just have to fill up this matrix and invert it. Now the problem, of course, is that...
What is the notation? Delta with 1 indexes.
Pardon?
Delta with 1 indexes, what it means? Yeah, no.
Here? This is...
No, left. Gauche, from your begin. Delta with 1
First
indexes.
expression on the
Chronograph
top.
symbol. Symbol chronograph.
Какой символ?
yes, it's a delta, that means...
С одним индексом, один дельта.
Here.
That means that this is a term that only occurs if I and j are equal.
But there is a
Дельта с
mistake.
одним индексом не очень...
Delta ij, sorry, this is a mistake. Yeah, this is a misprint. You're right. I didn't see it. Okay, you're right, this is a misprint. It's delta ij. Yeah, actually I have got it here. Yeah, this is a
You
misprint.
repeat it from time to time. And I have
No, you're right. This is a misprint. So I will correct this. So you can consider it as a matrix equation. Okay. So in that case, you have to fill up the matrix and invert it. Now the problem with this approach. So from the scattering point of view, it is completely exact. But of course, it is not a sparse matrix. It is a matrix where all elements, or almost all elements, are non-zero. That means that the size of the matrix, if n is the size of the matrix, you will need an n-square storage, and you will need to calculate the inverse an n-cube scaling. So that means that this approach is suited to low energies and small clusters. And of course, when you are allowed to expand this, into a series, you get exactly the equivalent. There is a third computing approach, but I will go quickly because it's not implemented into MSPec. So this is a partitioning approach which has been very popular in LEED in particular. So you do the calculation. You first start with a cluster of atoms for which you compute the T matrix, and then you add a second cluster and so on and so forth. But then I won't mention this because it's not in the code. But what is in the code is another approach which is called correlation expansion. It was devised originally in nuclear physics by the group of Thaler. It is a finite expansion. It is an alternative to matrix inversion or series expansion. And the important point is that it is always convergent. It's not a perturbative expansion, it's a combinatorial expression. So you can infer from the name combinatorial that you will have a lot of terms to compute, but it works all the time. And I will go, so basically you have an operator you want to expand. So I took A here, but in our case it will be either T or the scattering path operator. At the first order, you expand it in terms of 1 atoms, quantities related to 1 atoms. Then at the second order, you expand it in terms of quantities related to 2 atoms, and then you subtract some of the previous ones. And so on and so forth. So that, because it is a finite expansion, at the end you will end up with only 1 term. If you sum all the terms, you will end up with only 1 term, which is the full
result. You can calculate when you have crossover of atoms.
When you have?
You have some expansion in accord with in accord of number of particles.
Yeah.
If you have 3 particles,
yeah,
the main problem you must extract it, some crossover between the different EGK.
Yeah.
When you make your summation,
yeah,
you cannot do it. Because several AGK in volume are crossover. And so you take some interactions, you take in account twice, 3 times.
Yeah, and then you have to subtract them.
You cannot try some.
Yeah, this is a theorem, this is an exact theorem that has been demonstrated mathematically. I will give you the reference if you are interested. This is... it's one of these 2 articles. You've got an appendix where they demonstrate mathematically the theorem. So, in practice, I have not said anything about these quantities except that they depend on our atoms. So of course, the trivial way is to define it as the restriction of the operator A to the set of atoms. So if we do this, for instance, for T, the term Tij will be this type of expression. So this is an approach which is valid whatever the energy, and it contains the series expansion at the same order. So we've tested it at many different energies with different size of clusters. We found it is always more accurate than series expansion. It doesn't cost much memory. It converges all the time, and but we still need to speed up. But the important point is that there are cases where it is the only algorithm that you can use, because matrix inversion takes a lot of memory. For instance, the maximum I did with matrix inversion was, if I remember well, something like a kinetic energy for the photoelectron of about 300 EVs, a cluster of about 300 atoms, and for this I needed a memory of over 20 gigabytes to invert the matrix. Okay? So that means that you cannot go much beyond this. And it can happen, and we've seen recently examples where series expansion, even for kinetic energy of 200 EV, can diverge. So in that case, there is only this algorithm that can work. So once you've got the scattering path operator, you can model, you can describe with this a certain number of spectroscopies. So I show some of them here. Like if you want to model low energy electron diffraction or valence photoelectron diffraction, you need all the matrix elements of your scattering path operator. If you need to model photoemission, for instance, you need only these matrix elements, because you've got your electron which is excited on a given atom, which you know. If you want to model X-ray absorption, you need only these matrix elements, so this will be much faster and so on. And for instance, in the case of core electron energy loss spectroscopy, you need all three these types of matrix elements, but at different energies. Okay, no, this I skip, it's not very important. So here is some example of spectroscopies. So this is core photoelectron diffraction with the formula in terms of the scattering path operator. So here what happens, you've got your photons that excite a core level I on a given atom, which is the atom labeled 0. Then this electron can interact with all the system, and if I call J the last atom that it encounters before leaving the sample and being detected, then I can describe it by tau J0, and of course, as this last atom can be any atom in the system, you've got to sum over all the possible atoms. So this gives you in a straight way the formulation of the cross section from a small sketch. Likewise for the low energy electron diffraction. So you've got incoming electrons, which are scattered by the system, and you collect them outside. So if I label I the first atom encountered by my incoming electron, if I label J the last one, I just have to compute basically the scattering path operator before I and J, between I and J, and of course, as I and J can be any of the atoms of the system, I've got to sum over them. Okay, so this is all for multiple scattering. Now I come to the many bodies theory of core state photoemission. So this is the prolongation of work that was started, that was pioneered by Lars Edin back in the 80s, I think. Yes, I think this was probably the first article on the subject for photoemission and X-ray absorption. Then it was further developed by Takashi Fujikawa, and then with Takashi Fujikawa we are working on the implementation of this into the practical implementation of this into a computer code. So, excuse me. The photoemission cross section can be written like this. I'm sure that all of you are familiar with this this expression. So you start from an initial state I, which you excite through the optical transition, and you excite an electron through the optical transition operator. You've got the final state here. So you've got to take the square of this matrix element, the square modulus, and then of course you have to sum over all the final states that are consistent with the energy conservation. I think that's the end for this one. So the first step will be to reduce this, which is a many-body. These are many-body states. So the first step will be to reduce this to a one-body problem. So to a quasi-particle problem. So quasi-particle, it's basically a bare particle with some polarization around. What we'll be interested is what is called technically an electronic polaron, which is an electron interacting with a Plasmon field. Standard ab initio methods like DFT or GW, they can treat, of course, problems like this. They do not take the electron-hole interaction properly into account. So what we will do in practice, and this will have the advantage that it will blend very nicely with multiple scattering, we will impose it externally. We will add the coupling of to the Plasmon field as a perturbation, and we will treat it within scattering theory. So we will use essentially three approximations. So the headings, what we call blue electron model. We will go beyond the famous sudden approximation in ionization. And the way to treat this coupling will be done through the quasi-boson Hamiltonian. And thanks to these three approximations, we will be able to derive a workable formula, easy to incorporate into a computer code. Blue electron model, so that was proposed for this type of photoemission originally by Lars Edin. And by blue electron, he meant an electron which could be, to a certain degree, distinguished from the other electron left behind in the medium. And this is, of course, clearly a violation of the Pauli principle. So a typical example of what we could call a blue electron in Hedin's words is the photoelectron, which is ejected in the photoemission process. When its kinetic energy is large. When it's large, you have no way to mistake it for one of the other electrons in the system. So we will neglect the exchange coupling between the photoelectron and the electrons of the system because of this blue electron approach. So we expect a very small violation of the Pauli principle. So we will factor the photoelectron and the excited states of the system. So the n electron state, the star here, when in the rest of my talk, when there is a star, that means that it is in the presence of the core hole. So the electron has been excited and there is a core hole left behind. Okay? So the our n electron state can be decomposed into the excited state, so with the core hole, can be decomposed into the remaining n-1 electron system with a core hole in an excited state which I label I, and the blue photoelectron state. So the sudden approximation is just essentially you neglect the interaction of the photoelectron with the other electrons of the system. You suppose that the photoelectron is ejected at such a speed that you can neglect it. So in that case, you can write this state as this n-1 electron state plus the creation of the photoelectron, which you can rewrite like this. So you destroy, in your ground state, you destroy an electron, I, and then you create a photoelectron. Note that even in this approximation, which we'll not use, but even in this approximation, you take into account intrinsic losses, which are here, basically, because you've got your core hole here. Okay, so normally if you treat properly this state, you've got the intrinsic losses, but you don't have the extrinsic loss. So, in order to take into account the extrinsic loss, we go beyond this sudden approximation, And we use the Lippmann-Schwinger equation to write the states like this. So here we've got the states that here that corresponds to the sudden approximation, except that, okay, we add, you see this term here, which is not this one, which is neglected in the sudden approximation, okay, and which corresponds here, this is the potential that will describe the interaction between the ejected electron and the target. This is something we'll have to discuss, how to describe this interaction, okay? But with this scattering theory approach, we can take into account the coupling of the ejected electron with the rest of the system. So the next step is to describe the coupling. So this is the so-called quasi-boson interaction. It has been used essentially by Lars Edin in condensed matter theory, but if you look on the internet, actually, it's well known in nuclear physics, so I'm not familiar with nuclear physics, but it's used as well in this case. So what we will do, the excited Hamiltonian, so the Hamiltonian in the presence of the core hole, we separate it into the Hamiltonian of the n-1 electron system that contains this core hole and the coupling to the Plasmon field, HS star, the free electron ejected, and then the coupling of the free electron with the Plasmon field, with the rest of the system. Okay, and so we are interested into this coupling, which is characterized by boson-type excitation. This is why it's called quasi-boson interaction model. So this term here contains the intrinsic description of the intrinsic effect, Plasmon, and this term will contain the effect of the extrinsic Plasmon. So this is exactly what we need. Okay, so if we go into more detail, so we will replace this Hamiltonian by the quasi-boson Hamiltonian, which is composed of 4 terms. So first, the Hamiltonian of the boson, so the Plasmon in our case, the Hamiltonian of the free electron, so free boson, free Plasmon, free electron, and then the coupling between the two. So here we've got the coupling between the ejected electron and the Plasmon, and here the coupling between the core hole and the Plasmon. And actually, these terms here, which are the coupling constants, there are matrix elements of the so-called fluctuation potential, which is given by this, and matrix elements between plane waves here for the photoelectron, and between the core state here for the core hole. Okay, so again, this is the intrinsic, this is the extrinsic loss. This will result in the intrinsic and the extrinsic loss. Okay, now we can we can express the ground state of HB, which corresponds to the no Plasmon state and no core, in terms of the ground state of the HB star, which corresponds to the this plus the coupling between the core state and the valence electron, and through this canonical transform. Okay, so it's not well. I don't go into the details, but it's not complicated to demonstrate. Exponential minus s, with s being an operator which is linear in the creation of Plasmon. Okay, this can be actually the trick to obtain this is just to diagonalize HB star, and this can be done by replacing BI by this, by doing sort of a translation here. Okay, so with this we can rewrite the photoemission cross-section we started with. Now, in order to simplify the notation, I will note Ti, the matrix element, which I want to express and to include into the code. Okay, So here I've just mentioned, but we won't use it, the different energies involved, the energy of the full system of the quasi-particle. But we will focus now on this term. So, as I said before, we add externally the coupling to the Plasmon field for the photoelectron. And we do this through the Lippmann-Schwinger, using a Lippmann-Schwinger equation. Okay, so we can rewrite this matrix element here like this. Okay, so this is exactly what I showed before. Okay, so this, of course, is an eigenstate of Hb star with the eigenvalue Hwi, the energy of the plasmon. So this is the covalence coupling, and which will describe the intrinsic losses. And this will be, of course, you add here the photoelectron. So this will be an eigenstate of Hb star plus the Hamiltonian of the free photoelectron with this eigenvalue. Now, in our case, you can derive exactly the same type of theory for excitation of an electron, photoelectron from valence states, but we are only interested in core states, so we can rewrite it like this. So we've got the core state. Okay, here you've got the excitation operator, and what are the basic difference in addition to putting the core state I've done is to restrict the potential to the one I'm interested in, which is the coupling of the photoelectron with the valence electrons. Okay. So when I do this, if we look at the previous expression, yes, here. So what we have G, okay, which is an n-body. Propagator, an electron propagator. So this we do not know it exactly, so we'll have to make some approximations. And we've got, in addition, n-1 matrix, n-1 electron matrix elements to compute. So when you deal with this sort of problem, well, probably many of you know that one elegant way and powerful way to do it is to use Feshbach operator technique to reduce a many-body problem into a one-body problem. So we separate our space into a photoelectron space and a valence electron space by introducing these projection operators. So I won't go again into the details, but P describes the projection onto the valence states. Okay, I will not either like this or like this, these P, A, Q, so projector P and Q is one identity minus P. When you do this, you can end up quite quickly with this equivalent form, where here I've got only the PQ projection of the coupling, and here the QQ projection of the matrix. And the important point is that here, what appears here, when you do this reduction through the Feshbach process, what appears here is a one electron wave function, a one electron state, which is given like this. And for those of you who are familiar with what I introduced before, the Muller wave formulation of scattering theory, this is nothing else than the Muller wave operator corresponding to the sigma I potential. And so this is a one electron, and it satisfies this one electron equation. Okay, so this is called the optical potential or the self energy. So we have we have introduced this self energy optical potential, which is, you see, an average over valence states. Okay, so it is an operator in the photoelectron space. This is why you've got only here the photoelectron. Okay, it is an operator in the photoelectron space. It contains. This is important for us because so far I have not mentioned multiple scattering, of course. It contains the effect of the potential of the material. So it contains this this will contain the effect of the multiple scattering by the atoms. Another important point, I don't know if you remember, but we started from this initial state, which represents the n-1 valence electrons before the electron core electron is removed. So this is Cn, so this is equivalent to this. You have removed one electron. So this is the ground state of Hb. And so far what we had was the ground state of Hb star. Okay, so I remind you that we derived a way to pass from the ground state of Hb to the ground state of Hb star. Okay, which was through this exponential minus s. Okay, so just very quickly through the notation, because to go further I will need to take matrix elements of this this operator here. So I will note it Sj, and when I do this, I end up with a formula which involves only here the one electron dumped, the photoelectron, one electron dumped state, okay, and then these operators, which is a sort of average over the valence states of this quantity, okay. So we've got, you recognize the scattering, the Lippmann-Schwinger type of approach. So we can decompose it into two parts. The first part, you remember, if I don't have this, I've only the intrinsic contribution. This is, if I don't have this, I'm in the sudden approximation. Okay. So this one is the intrinsic term, and the extrinsic is the second one. So we've almost reached the end, because we will very soon have practical formulas to compute. Now I remind you that this dump photoelectron state can be written in terms of the Müller wave operator like this, and the plane wave, free electron state. Then I introduce this the identity as the product of the two opposite translation operator. Okay, if I use this property of the translation operator, I end up with this formula here, which is the first of my practical formula, where this quantity here I've indicated 0 to say that the wave function here is centered on the absorbing atom. So the 0 is for the absorbing atom. Okay. I didn't put C because there is already C here. Okay. So this is my first result. So I've got. So basically, this is my multiple scattering wave function. So actually, this is basically what I compute when I do just normal photoemission. So in addition, I've got this, and I've got this term which describes the intrinsic dumping, the intrinsic loss. For the extrinsic, I will make a further approximation, which is, because it's simpler, but it's straightforward to go beyond. I will suppose that my electron excites only one plasmon before exiting the sample and reaching the detector. So if it excites only one plasmon, I will, instead of having Tij, I'll just only 0 here. If I introduce the propagator, which I introduced before, which is defined by this with the optical potential, it's quite, well, not straightforward, but it can be demonstrated that the extrinsic contribution reduces to this. And this is very rewarding, this formula. It's not practical yet for calculations, but it is very rewarding, because it means that you have a core state, you excite the core state. Then the electron propagates until it interacts with the fluctuation potential and creates excitoplasmon, and then it goes out. Okay, so a very simple approximation. And once you have this, okay, there is a small trick that we can do. I won't go into the details, but we can rewrite it into a workable formula, which is like this. And now, if I want to summarize, I can rewrite my matrix element like this. So here is my photoemission like matrix element, and it is multiplied by this sort of damping, which involves the fluctuation potential and this function. So in this function you recognize two terms. This, the wave function of the core, so that will give you the intrinsic part of tau, of t, and here you will get the extrinsic part. Okay, so the last step is to introduce the loss function. And once we have introduced in terms of this GI, once we have introduced this loss function, we can write the photoemission peak like this. So usually when we do photoemission, this is what we compute. Okay. We have in addition the intrinsic loss here. And we can write the Plasmon peak as the photoemission peak, the value, the cross-section of the photoemission peak times this loss function at the energy of the plasma. So that means that we've got all the ingredients now, because this describes the core peak and this describes the first Plasmon peak. So now we just have, the only thing which is left is to compute this loss function. So there are basically two ways in the literature to do it. We can do it from fluctuation potentials, this is what I've mentioned before, or we can relate it to the screen-Coulomb interaction. So far, people have always used the first approach, and they've used model potentials, model fluctuation potentials in order to calculate the loss function. In addition, here you've got the function fc, which takes into account the intrinsic and the extrinsic part. People have always replaced this by a delta function. The core state just replace it by a delta function, and replace this photoelectron state by a plane wave. So what we will do in the code, because MSPEC computes exactly the core state and the multiple scattering wave function, so we will use them to obtain an accurate value of fc. And those of you who use ab initio code, they know that they know that the most ab initio code compute the screen-Coulomb interaction in the reciprocal space. Once you've got the Coulomb interaction in the reciprocal space, you can reconstruct it in the real space like this. And that means that if we introduce this sort of Fourier transform of fc, we can write this loss function, which is the only missing ingredient in our formula. In our formulation, we can write this loss function in terms of this Fourier transform and this that we will get from an ab initio code. So at the moment, so I finish here. So I've presented a multiple scattering approach to the calculation of the cross-section of one Plasmon loss photoemission. The interesting point is that the quasi-boson Hamiltonian can be incorporated in a natural and flexible way within the multiple scattering formalism. Extension to two Plasmon is straightforward. Actually, what I have done is multiple scattering of the photoelectron by the atom plus single scattering by Plasmon, by the fluctuation potential. But I can do double scattering by the fluctuation potential, and I will get two Plasmon lost. We are currently implementing this scheme into the MSPEC code. So this work has been funded by MSNano and EUSpec. And just my last slide is to thank the people I'm working with on this. So for the theory, there is Keisuke Atada, who is my postdoc, and Driss Arnaud, who is who is working on electronic structure methods, and he's a user of the Abinit code, so he's the one who will provide us with the screen-Coulomb interaction. I'm working on this as well with Takashi Fujikawa and Kaori Niki in Chiba University in Japan, and actually this undergraduate student Nobuyuki Tamura is helping us on the project to extract the screen-Coulomb interaction and to in the reciprocal space and to compute the Fourier transform. And the experiments are already available. They are performed by Christian Godet in our group, and with his collaborators Denis David and Victor Mansir, who is a PhD student from the University of Bahia in Brazil. So as I promised, it was long, but I thank you for your attention.
Question, please?
I have a question. Yes, you have skipped the point about the licensing or obtaining this software. How can someone...
It's, you just ask me, that's all, it's free.
Ah.
You just ask me, and if you are interested, I advise you to come to the training school. But Vladislav here is going to install it on his computer. We are working together for this on photoelectron diffraction, not on Plasmon loss, but it's no problem to obtain it, and it is free software. I only believe in free software. So I'm still here until 18th of March, so you can come to, so I'm just 2 floors above. You can come to my office if you want, and you can, if you are interested, no problem.
You mentioned that currently the work in progress is to implement the import of the potential from VASP.
From any code, yes, from VASP,
So
yes.
the question is actually, what is the difference of importing, to make it possible to import from any code? What is the current?
This is a very good point, because basically I would say there are two types of electronic structure codes. There are the one that compute a true potential, like Vin2K, like KKR, and there are those that compute a pseudo potential, like VASP, like quantum espresso. And pseudo potential is a problem for us because we need the real potential. So that's been a big issue, and I'm very happy that not me, but my colleagues, especially Keisuke Atada and another colleague, Peter Kruger in Japan, a Chinese PhD student, Shu Junxing, and Rino Natoli have solved it, the way from the pseudo potential to obtain the true potential. And now we have just published a paper in computer physics communication to describe an interface package that takes the information, the charge densities from VASP, and then reconstruct the potential, the real potential, the true potential, so that we can use it to compute our T-matrix elements, to compute whatever we need in the multiple scattering norms. But this is the problem. So very soon there is a PhD student from Munich who is going to come to make the interface with the KKR code of Munich, but this is easy because it is a true potential. The big jump was to be able to do it from VASP. So now that we've done it for VASP, I think for Abinit or other codes like this, it will be easy but this was the problem, and this is why it took so long, and we needed actually this huge collaboration. It was done within the EUSpec network and MSNano network. We needed this huge collaboration to put people from many different areas together and to work on the same problem. And now, fortunately, it's solved. So we will be soon able to import potential from any ab initio code into our code, into our codes.
But in your code, you use Muffin-Din approximation.
I use Muffin-Din approximation. It's not in the package, but for photoelectron diffraction, there is a version that uses full potential. The problem is that you must really need it, because of course it's much more time consuming. If you are familiar with Moffin-Tin problematics, you know that, for instance, the T matrices are not diagonal anymore. So that makes a lot of problems. So it's not in the package because we still haven't published it with Keisuke Atada, but I can show you, if you're interested after, I will not delay everybody, but I can show you some results we did, comparison of full potential and Moffin-Tin potential on, that was on GeCl4. It was for photoelectron diffraction from GeCl4 molecules. And at low energy, actually, we chose the energy at which there is the most. We took the X-ray absorption, okay? X-ray absorption, we saw that around 7 eV, this was where was the big discrepancy between Moffin-Tin and full potential. So we did the calculation for photoelectron diffraction at this very energy, where there was the big discrepancy in X-ray absorption. And indeed, we find substantial differences in the results. So, if you are interested, there is a version, and if you are interested, Keisuke Atada will, at the training school, there will be training on his code, which is a full potential multiple scattering code. It only does X-ray absorption, but if you are interested, we can input quite rapidly the photo emission into, because it exists. Okay.